Moving on, figure 7.1 shows a circuit diagram that includes component X. So here we have a graphical representation of the circuit. Part A says state the name of the component X. So here we have a component X which carries the symbol of a resistor with a line crossed. This is the symbol of a thermistor. A thermistor is a passive electrical component whose resistance depends on temperature, and hence it's an amalgamation of two words, thermal and resistor, thermistor. Moving on, part B, the electromotive force, EMF of the battery is E. The switch is closed. The potential difference PD across the 30 ohm resistor is V30. The potential difference across the 20 ohm resistor is V20. The potential difference across the component X is Vx. State an equation that relates Vx to V30 and E and V20. So here we notice or we realize that the two components, that is the 30 ohm resistor and the component X, are both in parallel combination. This is because they both have the same terminals. Since they both have that same terminals and they are in a parallel connection, the voltage across each component must be exactly equal. So Vx is nothing but equal to V30. Moving ahead, the voltage across here is V30 as measured, and across this 20 ohm component, the voltage measured is V20. The voltage across this terminal, let's call it terminal A, and this terminal, let's call it terminal B, is the same as the voltage across the terminals of the battery. Let's call them terminals C and terminals D. So in other words, the voltage across terminals CD, which is the voltage of the battery, is equal to the voltage across terminals AB, which is the combined voltage of V30 and V20. Hence, we can write E as equal to V30 plus V20, or the equation Vx or V30 Vx, which is V30, can be written as E minus of V20. Let's move on to the next part. Here in the next part, we read the EMF of the battery is 6 volt and the resistance of component X is 15 ohm. Calculate the total resistance of the circuit. To calculate the total resistance of the circuit, we understand that there are two resistors in parallel. So when two resistors are in parallel, 1 by R total or 1 by R equivalent is equal to 1 by R1 plus 1 by R2. We could also use a simplified version of this expression, which reads R equivalent is equal to R1 times R2 divided by R1 plus R2. This, when substituted, the values gives us the simplified answer as 30, 15, 30 into 15 divided by 30 plus 15. 30 plus 15 is 45, which is 15 times 3. 30 over 3 is 10, giving us the equivalent value of 10 ohm. And since the other resistor, the 20 ohm resistor, is in series, for series combination, we have R equivalent as R1 plus R2, which is 10 plus 20, giving us the final answer as 30 ohm. Moving on to the next part, the ammeter reading is the value of current I, which is obtained from Ohm's law. I is equal to V over R. When substituted the value of V as 6 volt, and R as 30 ohm, we get the value of current I as 1 over 5 or 0.2 ampere. Moving on to the last part, the temperature of the component X increases. State and explain what happens to the ammeter reading. We know that for a thermistor, temperature is inversely proportional to resistance. So if the temperature is increased, the resistance of component X decreases. So if the resistance for component X decreases, the total resistance R total also decreases. And since Ohm's law predicts that current I is inversely proportional to R, a decrease in resistance will result in an increase in current. So this tells us that the ammeter reading increases. The ammeter reading, which is nothing but the current, increases.